Science, science, science in pajamas. Alright, you guys, so today we're going to talk about projectile motion. Now, before we do any of the problems, we should probably discuss what projectile motion is. Projectile motion. Now, what this kind of more or less boils down to is similar to free fall, except there's already some horizontal component. So remember, when we were talking about free fall, you said that there was maybe a flower pot was sitting at the edge here, and then it just fell off. So in that case, gravity was the only force acting on it. But what if there was a ball on top of a table and it was pushed and it started moving towards the edge? Well, in this case, it has velocity in the x direction, which means when it falls or when it reaches that end, it's not just going to go straight down, it's going to go whee! And it's going to end up a further distance away because of that initial horizontal velocity. Now, the interesting thing with this case is once it leaves the table, the only thing acting on it in the x direction is gravity. So we talk about, how far did it fall, or how high was it initially, or its velocity. We can always relate that back to the free fall equations. Well, if we want to find out how far it went away from the table, or what its initial speed was when it left the table, then we have to look at that in terms of the x equations. And we're going to have to mix and match these a little bit. And what I kind of mean by that, once it leaves the table, remember the flower pot? Remember, when it was in free fall, it experienced a constant acceleration due to gravity, right? So at each time interval, it increased by the same amount. Well, once this rolling ball leaves the table, it experiences the same constant acceleration downward due to gravity. Because gravity is pulling it downward the same amount of acceleration as the other object. What we notice is that, at least height-wise, they match up each second when they fall. But because this one had that initial horizontal velocity, it just fell farther away. So that's what we call when an object is launched horizontally. So projectile motion launched horizontally. And we're going to do a couple of these problems together. So, yeah. Let's start with what we were just discussing, a baseball. It rose off of a 1.2 meter high desk and it strikes the floor 0.24 meters away from the base of the desk. How fast was it rolling? Well, let's diagram this first. So here's our table. Here's the ball. And we know that the table is 1.2 meters high. We also know that it landed, so it went, not to scale, definitely not to scale. It landed 0.24 meters away from the table. So let's think about what we know in this equation. What are the knowns? Well, we know that the vertical displacement so the vertical displacement equals 1.2 meters. We know the horizontal displacement equals 0.24 meters. There's one more thing that we know. Remember, once it leaves that table, gravity acts on it. So we know the acceleration, specifically in the y direction, so as it's once it leaves the table, as it's coming down, the acceleration in the y direction is 9.8 meters per second squared. But what are we trying to figure out? Well, we're trying to figure out this. How fast was it rolling? So we want to know the velocity in the x direction. Well, we have a combination of y's and x values, and we can't put them all into the same equation, but we can use a couple different equations to help us solve it. So how do we find delta v based on what we know? All right, well, if I want to find the horizontal velocity, I know a good equation for that. Delta x divided by delta t. All right, I know delta x, but I don't know how long it took it to fall. So I need to figure out some of this equation. The x is 0.24. But I want to know how fast was it rolling when it got to that end of the table. So from here to here, nothing should have affected the horizontal velocity. It's the vertical velocity that changed, but nothing should have affected the horizontal velocity because nothing is stopping it in the horizontal direction. So as it's going this way, yes, gravity is pulling it down, but gravity doesn't affect its velocity in this direction. So I want to know how fast was it going in this direction. I know how far it moved in that direction. I need to know how long it took it to get from here to here. Well, luckily for me, that's the same amount of time that it took it to get from here to here. So as long as I have a way to figure it out using free fall, I can. And we do have an equation using free fall. Now I'm going to switch it up just a little bit. When we were talking about it previously, we used x, but I'm going to actually use y because we're looking at the vertical position. Equals 1/2 times the acceleration due to gravity times time squared. So far so good? Hopefully good. All right. Yeah, that's my socks. All right, so if this equation doesn't look quite the same, it's because we have a delta y in there. That's fine. When we're looking at motion in one dimension and we're looking at our free fall equations, we had an x there, change in x. And since, or it was, sorry, we just simply gave it the different connotation of delta y. So I'm moving around, kind of squeaking all over the board. So we're just simply changing the connotation of y instead of x because we're looking at the vertical movement. All right, I know how far it moved vertically. I know the acceleration due to gravity. I need to solve for time. So I can rearrange this, and that means multiplying both sides by 2 to get that canceled out. So we have 2 delta y equals a delta t squared. I can divide both sides by a, cancel that out, and we're left with t squared equals 2 delta y over a. And since I don't want that squared, square root that. Well, this I can answer. So the time would be square root of 2 times the vertical distance, 1.2 meters, divided by the acceleration due to gravity. Now, some of you are probably thinking, but Miss Komar, why are you not putting a negative sign there? Because technically it'd be negative for both of those, because it moved downwards. So its displacement was in the downward direction, which is negative, and the acceleration is in the downward direction, which is negative. Both of those would cancel out. Check that action out. All right, so we go through, we do that, we solve it, we get 0.49 seconds. Well, now we have a time. Now we can go back to this equation and solve for delta t. So how fast was the ball going as it was rolling forward? So the horizontal velocity equals change in x over change in time. They gave us the change in x, which is 0.24 meters divided by 0.49 seconds. And assuming I did my math correctly, it is 0.49 meters per second. All right. It seems complicated because we have to include y equations as well as x equations. But once you have more practice in identifying the knowns and working them together, it does become easier. Let's go ahead and do another one, shall we? All right. So next one. A pelican is flying a horizontal path and drops a fish from a height of 7.2 meters. The fish travels 8.6 meters horizontally before it hits the water below. What is the pelican's speed? So what that would look like, here we have the pelican. It's flying along this way, and he drops a fish. Now the fish still has the initial horizontal velocity the same as the pelican, because the pelican was carrying him. So the fish is also going to keep moving a little bit in the forward direction. Now, the pelican, 7.2 meters up, and the fish hit 8.6 meters before it hit the water. So what are knowns? Delta y equals 7.2 meters. Delta x equals 8.6 meters. The acceleration due to gravity is negative 9.8 meters per second. And technically that's negative 7.2. And we are looking for the speed of the pelican. It's just like the last problem we did. So first, we have to figure out time. And again, the reason for that being is the way to find this is going to be this equation here. Delta Vx equals delta x over delta t. I know the x, I want to solve for v, but I don't know t, so I need another equation. The time it took the fish to move from here to here is the same amount of time it took the fish to move from here to here. So once again, I can go ahead and use one of the free fall equations to help with the y direction. So let's take a look at this. We have, I'll put this over here. Delta y equals 1/2. Oh, bad papers. Yeah. Delta 1/2 acceleration due to gravity times time squared. Well, we've already rearranged that and showed you how to rearrange it in the last problem, so I'm just going to go ahead and have it ready to go. So 2 delta y over a equals square root of 2, and that is 7.2 over negative 7.2 because it's moving downward, negative 9.8 meters per second squared, and our time is going to equal 1.2 seconds. So it took 1.2 seconds for the fish to go from here to here. So that's 1.2 seconds to travel down, as well as 1.2 seconds to travel over. So that's our time. We can come back here now and plug that in. Delta Vx equals our x, which is 8.6 meters, divided by our time, which is 1.2 seconds, and we get 7.2 meters per second. So that is the velocity of the pelican. So not horrible. Not horrible at all, I hope. All right, we're going to do one more involving our pelican, then we're going to move on to our next concept. All right. So, still using the same pelican, it was traveling at the same speed. Remember, we just calculated that speed as 7.2 meters per second. So the pelican was traveling at the same speed, but this time he was only 4.5 meters above the water. How far would the fish travel horizontally before hitting the water? We'll go back to make our little diagram. Got the birdie, and we know, and he's carrying the fishy. We know that he is traveling with a velocity of 7.2 meters per second squared. This time he is only 4.5 meters above the water, and we want to know how far does he move before the fish hits the water. Alright, so again, just make it a little easier to read. Delta Vx equals 7.2 meters per second. Delta y equals 4.5 meters, technically negative 4.5 because it's going in the downward direction. We know the acceleration due to gravity is negative 9.8 meters per second squared, and we want to know delta x. Now this is going to be very similar, except when we solve for delta x, we're just rearranging that equation. So delta x would equal velocity times time. But once again, we need to find time. But we can find it the exact same way we did before. Isn't that awesome? So we have change in y equals 1/2 the acceleration due to gravity times delta t squared, or time squared. We've already rearranged this before. We're not going to worry about rearranging it again or showing you step by step how to do that. We're just going to put it into what it should be. Square root of 2 times the change in y over the acceleration due to gravity. That would be square root of 2 times negative 4.5. Again, it's moving downward. divided by negative 9.8, and we are left with a time of 0.96 seconds. We take our time, we plug it in over here. So delta x equals, we use the same velocity from the last one because it told us to, 7.2 meters per second. And we have 0.96 seconds. The fish traveled 6.9 meters horizontally before it hit the water. So that's how far it moved this direction. All right, before we completely move on, I do want to talk about one more kind of projectile motion. So we talked about motion when it is launched horizontally. What if instead of launching it horizontally, it's thrown at an angle like that? And if you were to take a baseball and throw it from one person to another, that's another kind of projectile motion. But instead of it just starting out at one certain height and moving downward, it's going up first and then moves downward. Now this does mean it's going up at an angle. So we're going to have to incorporate that into our calculations. And when we incorporate that into our calculations, that means using theta, when we talk about the x and y components, we're going to have to use sine and cosine of theta. So it does get a little more tricky, but it's more or less the same thing. It just looks scarier. So let's do a problem with this. A baseball is thrown at an angle of 36 degrees relative to the ground at a speed of 27 meters per second. If the ball was caught 59 meters from the thrower, how long was it in the air? So what are we looking for and what do we know? We know that the angle is 36 degrees relative to the ground. We know that it has a velocity of 27 meters per second. And we know that it was caught 59 meters from the thrower. So this is 59 meters. The angle is 36. And it has a velocity of 27 meters per second. Now, all right. We want to know the time. Now again, it looks scary. It even looks scarier than the projectiles launched horizontally, because now we got to deal with the angle of this. But the nice thing about it is it's going to use the same equations we looked at. We're just going to have to incorporate the idea of the angles into it. So remember how we use sine and cosine to figure out x and y components? We're going to use those in the equations to help us break down the x and y components. All right, so let's figure out t. One of our past, actually not one of our past, but one of the equations we've looked at was delta v equals delta x over delta t, right? And guess what? We can actually use that. You just have to modify it. Now the reason why we can use this is because the time that it takes it to travel this way is the exact same time it takes it to travel up and down. Because that's the time is how long it takes to go up and over, which is also from here to here. So we can use the time for both, or for a lot of different things, and time is always crucial. So I can look at this and I can rearrange it. And I know that if I rearrange it, first off, I'm going to get delta t on both sides. We can cancel it out. We get it out from the bottom. We are left with delta t times delta v equals delta x by both sides by delta v. Yeah, sorry. And then we're left with delta t equals delta x over delta v. However, this is looking at horizontal displacement, but this velocity is at an angle. Ta-da! So what we need is the horizontal component, the x component of the velocity. So what that would be is the initial velocity cosine of theta. Because we have to take into account, it's not going 27 meters per second straight horizontally, it's going 27 meters per second upwards at an angle. So we have to take that into consideration so we can find the horizontal component of it. So just like when we were resolving vectors. So we go through, we move 59 meters, the initial velocity was 27 at an angle of 36, so 27 cosine 36, and our time is 2.7 seconds. Could be more horrible, right? Could be a lot more horrible. Alright, I'm going to use the same idea, this same scenario, but we're now going to figure out how high did it travel. All right. We figured out the time was 2.7 seconds. I want to now know, using the same information, how high, what was the height at the peak of the ball. So now what I want to know is delta y. All right, so again, we've looked at some equations like this before. One of the equations that we've looked at was the final squared equals the initial squared plus 2a delta x. We've looked at this equation previously. However, I'm going to alter it because now we have to tailor it for this question. We're not looking at horizontal velocity or displacement. We're looking at vertical displacement. And since the velocity, again, was launched at an angle, we have to take that into consideration. Now, it was caught, so that means that the final velocity equals 0. But we still have an initial velocity. And that initial velocity was still at an angle, so we have to take that into consideration and use the velocity sine theta to look at the y component of the vertical component of the velocity. So the equation that we're going to be looking at now, if we were to first of all rearrange this to solve for delta y, it would be f squared equals, minus I squared plus 2a, divided by 2a. So all I did was take this and rearrange it. Now we said that because we're looking for the vertical displacement, we have to consider the vertical velocity. Now since it's caught, there's 0 final velocity. And the vertical component of the velocity would be VI sine theta squared. So we go through, it ends up being VI squared sine theta squared over 2a. Go through, plug it in, so that's 27 squared sine of 36 squared over 2 times negative 9.8 meters per second squared. And we are left with displacement of 12.85 meters. All right, so not too bad. Not too bad at all. So that was its height at its peak. All right. So I hope this helped you to understand a little bit more about projectile motion. If you have any other questions, feel free to hit me up in Classroom, Google Classroom, with email. I'll do my best to help you guys. You know I'm here for you. But until then, you guys just stay awesome, and I'll talk to you later. All right, you guys, take care.